Okay, let's start with the lecture. We have we are working on linear vector spaces, and let's continue with the lecture. So this is a part of course PH3103 at IISER Calcutta. So we have looked at the definition of linear independence, and we also have given some example of vector in two which are linear independent as well as orthogonal. Let us go and see more examples. Let's look at the example which are linearly independent but not orthogonal. It's very easy to construct. You just take a vector here, the example uh, with the vector v with the component v1 and 0, and vector u with the component u1 and u2. It is easy to show that they are linearly independent, and they are not orthogonal unless u2 is 0. So it's a simple example. Let's consider an example other way around. Let's look at the vector and see what happens if they are linearly dependent. That means let's consider two vectors uh, v and u with the component v1, uh, v2 and u1, u2, and see what happens when they are not linearly independent. So let's first check the combination alpha into v and beta into u. Of course, we have to use our definition of multiplication by a scalar and summation of two vectors. By combining that, we have to equate that to a zero vector. So that is what it means to be showing the linear independence or linear dependence. So it turns out to be a two decoupled equation in terms of alpha and beta, u1 and u2 and v1 and v2. The alpha into v1 plus beta into u1 equal to 0 comes from the first component, and alpha into v2, beta into u2 comes from the second component. Both of them have to be 0 irrespective of values of alpha and beta. Let's use the first equation and establish a relation between alpha and beta with the component u1 and v1, and take that and substitute in the second relation constraint coming from the second component, and we can simplify this expression to get minus beta into v2 by u1 divided by v1 plus beta u2 equal to 0. Since beta is equal to not 0, the other factor which multiplying them have to be 0. From this condition, we get the relation u2 in terms of v2, that is u2 equal to u1 by v1 v2. This we can substitute back into u, and we see that after some trivial simplification we get u as u1 by v1 into vector v. So this simply shows that if the vectors are not linearly independent, then they can be related to each other by some relation. So that is exactly what we are trying to show, that if the vectors are linearly independent, then no such relation is possible. So that is one of the goal of this exam. Let's uh, go to the concept of basis vector, which is a very important idea both in mathematics of vector spaces as well as in physics. Uh, let's state the definition. A basis of a vector space V with the vectors VA is a minimal set of linearly independent vectors EI that spans the complete vector space. Let's quickly remind you what is the meaning of spanning a vector space. The spanning of vector space means that every element of that vector space should be expressible as a linear combination of these vectors EI. Now that means that any arbitrary vector VA can be expressed as a sum I 1 to n AI, some coefficient, into a basis vector EI. This should happen to every element of vector space. The set minimal, it means that if there exists another set which also spans this vector space, they are also linearly independent, then there should be less than or equal to the number of element in the Fi. The minimal set means that if there is another set F of J's which are also linearly independent and spans the vector space, then the number of elements in the basis EI should be less than or equal to the elements of the set Fj. So that is to say that F is a larger set than the E itself. So the idea of basis element is that every element of vector space V can uniquely expressed as a sum of basis element, that is VA equal to sum I going to 1 to n AI EI. So this is what is the advantage. One don't have to keep track of all the element. It is sufficient to keep track of basis element. Then all the element of vectors can be expressed as a linear combination of these basis vector. Basis elements need not be orthogonal to each other, but they necessarily have to be linearly independent. Basis set of a vector space need not be unique. A vector space can have many basis set or as many as basis set as possible. It is always possible to relate or have a unique relation between the two basis sets. The number of elements finite, then it is called dimensions of the vector space. If there are infinite number of elements in the basis vector, then the dimension of vector space is infinite. Okay, let's look at some of the examples for the basis vector. Let's take our standard R2 and then let's construct the some basis. So here all the elements of the R2 are represented by two tuples V1 and V2. It is easy to show that two vectors E1 is equal to 1, 0 and E2 equal to 0, 1 are linearly independent. In fact, we have already shown that it is not 1 in that case, it had some other number V1 and U1. but you can normalize them to get this E1 and E2, and they are linearly independent. Every element of R2, which is given as a two tuple V1 and V2, can be written as V1 into 1 0 plus V2 as 0 1, or V1 into E1 plus V2 into E2. Here V1 and V2, we call them as a component along the basis, and the E1 and E2 are the basis vector. One don't need to have any more vector element to describe all the element of R2, so is to say that these form the complete set, or they can span the full R2, so they form the basis. Now here is the homework which you put along with your notes when you submit it. You also have to solve this homework problem. The homework problem gives that show that the following vectors also form a basis for R2. The vectors are G1 is equal to 1 comma 1 and G2 is equal to 1 comma minus 1. Given two bases, there exists a unique relation between them. So now we have two bases, EI and GI. You have to establish a relation between them. This is a part of the homework. So you can write it along with your notes, which you will have to submit, and I will look into. We have seen that a vector space can have several bases, and not all bases need to be a orthonormal. There are certain advantages having an orthonormal basis. Basis element of a vector space are orthonormal. Finding the component becomes simpler. Let V be the vector expressed in terms of an orthonormal basis. Bases are orthonormal, then we should be able to write it as a I dot Ej is equal to delta Ij, where delta Ij is called the Kronecker delta, which is 0 if I is not equal to j, and it is equal to 1 if I is equal to j. So this is essentially a identity matrix. All the element along the diagonal are 1 and all the off diagonal elements are 0. The vector is expressed in terms of the basis element with the component vi. Now take a dot product with the basis element ej, and that would be v dot ej, and we can show that v dot ej is essentially this quantity, which is a delta ij, and this summation would be simply result in a vj, and that is a component along the basis element ej. So this becomes get far complicated when the basis elements are not orthonormal. One need to find the component using a proper matrix inversion method. So here this delta ij, which helps us to do this summation without going through any of the complicated computation.